Okay, for this video, I'll be going through chapter 19, Pure Physics, Electromagnetic Induction, Success Criteria D and E. So for D, it is to describe the structure and principle of operation of a simple iron core transformer, okay, as used for voltage transformation. And E is to recall and apply the equations as shown to new situations or to solve related problems for an ideal transformer. But of course, we will also talk about real life transformer. So actually, why do we need to talk about transformer? So we will actually have in this chapter, we started off with a force, okay, and also an external magnet. So if we have a conductor that is that we apply a force on it, okay, in the region of an external magnet, so it will experience a magnetic field. And because if we let the conductor rotate or the coil rotate, it will experience a change in external magnetic field lines, okay, and therefore there will be induced current. Okay, so we are actually able to produce current, but so how are we actually going to get this current to the consumer's home? So this is the part whereby we will have cable lines, okay, that is joined from the power station to the homes of the consumer. Okay, so why do we need a transformer? Let's find out. Okay. Okay, induced EMF or current can be generated in a coil by a changing magnetic field produced by another coil carrying a direct or alternating current. So before that, we were having the conductor move in an external magnetic field to let it experience a change in magnetic field. So as long as the conductor experiences a change in magnetic field, okay, it doesn't matter whether it is moving in a external magnetic field, or we can actually use the magnetic field produced by a current. Okay, so take note, the coil that's producing the magnetic field is called a primary coil, but the other that is producing the induced current or EMF is called a secondary coil. So let's see how this goes about. So what if we use a coil that carries direct current? So this direct current, when current flows, it will produce a magnetic field. Okay, so if we have a coil that is near this primary coil, then it will experience a change in magnetic field, and therefore there will be an induced current. So we have the structure looking like this. When the switch in the primary coil is closed, so we use a direct current. Okay, current flows. Okay, the current flows in this way, and according to, if we close the switch, the current flow, and by using our right hand grip rule, okay, for solenoid, okay, then there will be a north pole on the left hand side and a south pole on the right hand side. So before the switch was closed, there was no, before switch closed, okay, there was no magnetic field, right? Because no current will flow. Yes. So the secondary coil, which is placed over here, will not experience the south pole. But once the switch is closed, it will experience a changing magnetic field, a change in magnetic field, from no magnetic field to now it will experience a magnetic field. Okay, so if over here is a south, then there will be a south, because from no south to having a south pole experience, then according to Lenz's law, there will be a south pole here. So if it's a south pole, then I can actually map out the direction of the induced current. Okay, induced current. So then there will be induced current flowing, and therefore the galvanometer will then register a deflection. Okay, so this is what is being said here. When the switch in the primary coil is closed, current in it flows, right? When current flow, you produce a magnetic field, and then there will be an increasing magnetic field produced in one direction because it's direct current, and this increasing magnetic field will produce an induced current in the secondary coil that is shown by a deflection in the galvanometer. But after a short while, really very short while, as the current in the primary coil is constant, the magnetic field in the coil becomes steady. Okay, so there will be no change in the magnetic field, which is very important. Then according to Faraday's law, there will be no induced current. Therefore, the induced current in the secondary coil stops. This explains why the pointer of the galvanometer will return to 0, because there's no longer a induced current. Okay, so I can then turn on or open up the switch. So when I open up the switch, current stops, right? So from having a magnetic field to no magnetic field. So the magnetic field from earlier starts decreasing in the opposite direction, and induced current will now be produced in the secondary coil in the opposite direction. So why is it in the opposite direction? Because previously there is a south, okay, but now that I open up the switch, okay, there will be no more current flowing, so there will be no south pole produced here. So no south pole produced, then this will become a north, so as to resist the south that is sort of leaving it. Therefore, the direction of the current will now change, and now the galvanometer will register a different direction. Okay, so the pointer of the galvanometer will then point in the other way before coming to rest, because once the switch is open, there's no longer current flow in the primary coil, there's no longer a magnetic field, so there is no change in magnetic field experienced by the secondary coil. Okay, so take note, the soft iron core is used to concentrate the magnetic field lines to make the magnetic field stronger, so as to produce a greater induced current. Okay, but then even without the core, there is still an induced current produced, but smaller. So how can I make sure that there's a continuous current, or there will be a continuous induced current in the secondary coil? I can have someone to open and close the switch, open and close the switch continuously. Okay, so as to create a magnetic field, and when I open the switch, no magnetic field, so that the secondary coil will experience a changing magnetic field. But of course, this is not practical. So how about we have AC? Okay, so now AC, you know that the direction of the current changes direction. So maybe I close the switch. Okay, so because it's AC, so let's say for this cycle, the left hand side is positive, the right hand side is negative, so current always flow from higher potential to lower potential. So let's say the current flows this way, and then I use my right hand grip rule for solenoid, and my current that's flowing in the primary coil will produce a north and south as shown like that. So to the secondary coil, suddenly there is a south pole being produced here. So according to Lenz's law, there will be a south pole here and north pole here by the induced current, because there is a changing magnetic field. According to Faraday's law, there will be induced current, and this induced current will flow in a way so as to oppose the change producing it, which is under Lenz's law. So there will be a south pole to provide some kind of resistance. Okay, so this is for the when this is positive, and when the left is positive and the right is negative, alternating current. But half a cycle later, there will be switch in the polarity. So now the current will flow this way, will change direction, and therefore the direction of the magnetic field or the poles will then be switched south and north. Okay, and if it now becomes like this, then over here it will become a north so as to oppose it, and it will become a south. So the galvanometer will keep changing direction, Okay, so this is like what is being said over here. Okay, so as the current in the primary coil alternates, right, positive on left, negative on right, and then half a cycle, negative on left, positive on right, because it is an alternating current supply. Okay, the induced current will also alternate and with the same frequency. So if the frequency of the current supply is low, the pointer will move left and right at regular interval. But if the frequency is high, the pointer will remain stationary, right? Because it's not fast enough to reflect the change. So this pointer will be seen to be vibrating in its position, trying to go left and right at within a short period of time. Okay, so what's the purpose of the soft iron core? It is to concentrate the magnetic field produced by the current in the primary coil. Okay, concentrate the magnetic field. Okay, and please take note that the current do not flow in the core. Okay, it is the magnetic field that is moving in the core, right? That's why you use soft iron. So the wires here are actually made of copper, and they can be actually insulated, of course. Okay, so if I were to stretch this core like infinitely to a very long distance, the magnetic field will actually flow in the core, right? The magnetic field lines will actually be flowing in the core, but the current can still be produced in the secondary coil, even though the core is very, very far away. Okay, so that is how amazing it is. There is no direct connection between the wires, but the current will still be induced on the secondary coil. Okay, so please take note that it is not the current that flows through the iron core. It is a magnetic field, and because the magnetic field changes direction, there will be induced current in the secondary coil. Okay, so this is the working principle of a transformer. Why do we need a transformer? Different voltages are needed for different electrical appliances at home. For example, for handphone charger, okay, we are using a low voltage. For TV, we are using higher voltage. Okay, but the standard voltage applied to our home is 240 volts in Singapore. Okay, so sometimes we need a transformer to change this voltage to a lower voltage or become a higher voltage. So a transformer, if it steps up the voltage, it is a step-up transformer. If it decreases the voltage, then it's a step-down transformer. So this is Faraday's induction ring experiment. So he actually uses a DC current. So this is positive, negative, right? The longer is positive, so current flows out. When the switch is closed, the current will flow in this direction. So we trace it out. Then we apply right hand grip rule. Okay, so it will be a north here, and coil B is a secondary coil. Coil B actually experience a change in magnetic field. How so? Because when the switch is closed, coil B experience from zero magnetic field to having a magnetic field when the switch is closed, right? So because over here is a north, then according to Lenz's law, this will be a north so as to oppose the change producing it. Therefore, the current will be flowing by using right hand grip rule, yeah? The current will be flowing in this direction. Okay, will be flowing in this direction. And again, I must say that there is no current flowing in the iron ring. No current flow in the iron ring. Very important. It is the magnetic field lines that is flowing in the iron ring or iron core. Okay, so then there will be the compass movement. Okay, so Faraday observes that when the switch was closed, the needle of the compass deflected in one direction and returned to its resting position. Why does it return to its resting position? Because after the switch is closed, he was using a DC circuit, DC current. Okay, there will no more change in magnetic field, right? The current becomes stable. The magnetic field produced by this current, it is stable, so the coil doesn't experience a change in magnetic field anymore. So there will be no more induced current after a while, and so the compass returned to its resting position. But when the switch was closed, now the switch was open, the needle again deflected momentarily. Why? Because from having magnetic field, it experienced a magnetic field, and now the switch is closed. Now there's no longer a magnetic field. From magnetic field to no magnetic field, there is a change in magnetic field. So it will deflect, but it will deflect in its opposite direction and then go back to the resting position. Okay, the closing and opening of the switch caused the magnetic field in the ring to change. Okay, and the strength of the magnetic field increases as current flows into A and then decreases as the current flows to 0. Okay, so these changes in the magnetic field induce a current, Faraday's law, flowing in coil B and cause the needle to deflect. Okay, so when the switch is closed, the induced current in B generates a magnetic field that opposes the increase in current in A as described by Lenz's law. Okay, so therefore, this is to tell us that the compass will deflect in different direction as you open and close the switch. Okay, so this is how transformer work. So it is something like what we have done here. Okay, just that now it is the iron core is shaped into a shape of a ring. Okay, so what is the structure of a transformer? It consists of 3 parts, mainly the primary coil, laminated soft iron core, where the magnetic field lines will be flowing inside, and then we have the secondary coil. Okay, so step-up transformer, we have for O level, the primary coil is always on the left hand side. The secondary coil will have the will be on the right hand side. Step up means your voltage increases. We step up the voltage. Step down means the voltage decreases. And again, primary coil on the left hand side. Secondary coil will be on the right hand side. This is the convention for O level. Okay, so we have step up and step down. So as you can see in the primary coil, the number of turns is lesser. In the secondary coil, the number of turns is more. This is for a step up. For a step down, the primary coil, the number of turns is more. The number of turns is lesser for the secondary coil. Okay, so we have a laminated soft iron core. It reduces the transfer of energy to the internal store by eddy currents. Okay, these are currents which are local induced electric currents that flows in the loops. Yeah, because actually this is also a metal, it will experience a change in magnetic flux, right? So there will also be current flowing inside. Okay, so these are called eddy current. But because we have lamination, we have let me see if we have the diagram. Okay, we don't have it. So instead of using one entire piece of iron, we have sheets of iron. Okay, we have sheets of iron. This is one sheet, it's very thin, and to the next sheet of iron, we actually have a laminated core in between. So that the current do not flow from one sheet to the other. Okay, so we minimize the transfer of energy to the internal store due to this eddy current, okay, by this lamination. Okay, so this will make the transformer non-ideal. The ideal case is that there is no eddy current. Okay, now without lamination, large eddy currents are actually produced and the transfer of energy to the internal store will be much larger. Okay, why do we use soft iron? Because soft iron is easily magnetized and demagnetized. Okay, so why do we need that? Because this is a low AC voltage, right? So the direction of the magnetic field lines will change. It will be north and south in one cycle, then south and north in another cycle. So we want the magnetic domains in the iron core to change rapidly. That's why we use a soft iron. Okay, so what is the purpose of the soft iron core? It is to concentrate the magnetic field lines within itself. So this improves the magnetic linkage between the primary and the secondary coil. Okay, take note, the changing magnetic field lines in the primary coil is linked to the secondary coil through the soft iron core. This is the principle behind it. The changing magnetic flux will then induces a voltage and therefore a current on the secondary coil. It is a chain, it is a magnetic field lines that is flowing in the iron core and not the current, although now we have eddy current but it's very minimum. Okay, so it is the magnetic field lines that link the primary and the secondary coil, and this will result in an induced EMF and then induced current in the secondary coil. So this is how energy is being transferred from the primary coil to the secondary coil. Okay, now the working principle of a transformer: when an input alternating voltage flows in the primary coil, it will produce a changing magnetic field in the soft iron core that's linked to the secondary, and the magnetic lines of the magnetic field then cuts the wire in the secondary coil, therefore it produces an induced voltage. Okay, so when the induced voltage changes in its direction in the primary coil, the magnetic field in the soft iron will also change the direction. So now the magnetic field lines cut the secondary coil in the opposite way. So the induced voltage changes direction as well, and therefore we have alternating voltage. Okay, so in summary, the primary coil converts the input voltage into magnetism in the soft iron core, which then produces output voltage in the secondary coil. So the linkage between primary and secondary coil is by the magnetic field lines. Okay, so how do we produce all these magnetic field lines? We actually have a voltage, AC voltage, because the direction of the current changes, right, constantly. Therefore, the magnetic field lines will also change constantly. So where does the input come from? The input comes from our generator, because the generator is actually able to produce AC voltage. Right, we have done our AC generator, so the generator will actually be fed to the input of the transformer, so that the output will also be a AC voltage. Okay, I hope you see that we are building part by part to it. Firstly, we have the AC generator, right, and it produces a AC voltage. Then this is linked to a transformer, and the secondary coil will then actually produce a AC voltage. But why can't we just use the generator by itself? Okay, because sometimes we need to step up or step down the voltage. Okay, later on this will be covered in our power transmission. Okay, but let's look at how the voltage of the primary and secondary coils are related. Okay, so this is the first formula that you need to know. Vp over Vs equals to Np over Ns. Vs is the secondary voltage. Vp is the primary or input voltage. And Ns is the number of turns in the secondary coil. Np is the number of turns in the primary coil. You see that it is linked directly. Vp, it is actually equals to Np, and Vs is equals to Ns in the numerator and denominator. Okay, so for a step up transformer whereby Vs is greater than Vp, therefore Ns should be greater than Np. Right, if I want step up, my Vs must be higher, therefore my Ns must be higher than Np, and my Vs must be greater than Vp. But for a step down, the secondary voltage will be smaller, which means Vs less than Vp, right, stepping down, and therefore my Ns must be less than Np. Okay, of course if we put in numbers it will be easier. Later on we'll do some practices. Okay, so will we have Ns equals to Np so that Vs is equals to Vp? No lah, then it defeats the purpose of a transformer. So transformer is either step up or step down. That means if you want the voltage to be higher in the secondary, we use a step up. If you want the voltage to be lower in the secondary, we do a step down. So what's an ideal transformer? For ideal transformer, the power on the primary is equals to the power on the secondary. So I have PS equals to PP. And what is power? Power is actually voltage times current. So I have VSIS equals to VPIP. And if we arrange this equation, we see that Vs over Vp is equal to Ip over Is. So this is different from our Vs Vp equals to turns ratio and SMP. It is sort of direct, right? But because the power is constant, very important, in the power in secondary is equals to power in primary. Therefore, we have this relationship, and therefore my Vs, if is large, then my Is is low. If my Vp is low, my Ip is large. Okay, so expressed in terms of turns ratio, what is turns ratio? It is MP over Ns. In terms of turns ratio, we have this relationship. Okay, so we can see that as the output EMF increases, the output current decreases, and vice versa. This is important because P power equals to I multiplied by V. If the V is increased, the current is decreased. Okay, vice versa. If the V is decreased, then current is increased because they should have the same P. Okay, ideal transformer. But in reality, transformers are not ideal. Okay, so the output power will be less than the input power. So we have this term efficiency is defined as the ratio of the output power over input power. So maximum is 100% or having efficiency of 1. Okay, we cannot get more than 1. If it's more than 1, then nobody needs to work already. Okay, so in a case whereby the transformer is ideal, efficiency ratio is 1 or 100%. Okay. So we still haven't done any application yet. We will see, because actually some of you will be wondering, so why do we need a transformer? Okay, why do we need to step up or step down the voltage? And this will be covered in success criteria F.